Welcome to our paper SimNP, Learning Self-Similarity Priors Between Neural Points. We tackle the task of single and few view 3D reconstruction. This means, given as few as a single image at test time, our approach aims to reconstruct a 3D representation which we can render from novel views. Therefore, we learn a category-specific prior at training time. However, our approach is general, as we do not make any assumptions about the category at hand. Considering related work, we find that there is an inherent trade-off between the data prior and the observation. Previous approaches like scene representation networks learn overly strong priors by modeling the entire function space of a category. As a result, they generalize poorly to new instances, if they are underrepresented in the training data. On the other extreme of the spectrum are nerve-like methods, which do not learn a prior at all and therefore fail in reconstructing unobserved areas. With SimNP, we aim for a lightweight prior in form of category-level self-similarities. At the heart of our method is a neural point representation that is comprised of a point cloud with attached feature vectors. We tackle the point cloud prediction separately. We factorize the point features into instance-specific embeddings and category-level attention scores, mapping the embeddings to point identities. Additionally, we concatenate per-point shared features that learn a basic category template. During training, we optimize all components, including a rendering decoder network, to reconstruct multi-view training examples. With the help of our learnable attention scores, we enable our neural point representation to share information in form of the learnable embeddings between similar regions of the category. After training, we freeze all shared blue components and only optimize the instance-specific embeddings to reconstruct the observations of new test instances. Because our attention map has learned to share information, this sparse supervision at test time is enough to enable rendering of novel views. We employ a similar autodecoding approach to obtain coherent point clouds. With coherency, we describe that each point has an identity that should be consistent over different instances within the category. For example, if a certain point is at the left wheel of a car, it should be at the left wheel for every other car. We achieve this by learning a deformable point cloud template in form of a bottleneck MLP conditioned on instance-specific learnable shape embeddings. During training, we minimize the chamfer distance to ground truth point clouds. In order to have a supervision signal for the shape embedding at test time, we additionally train an encoder with the same decoder to output the same point cloud. Furthermore, our formulation is flexible enough to allow for additional optional supervision signals at test time in form of the segmentation mask or depth maps. Looking at qualitative results for single-view reconstruction, we can see that our lightweight prior generalizes much better to uncommon appearances like color variations underrepresented in the training data. Unlike previous approaches, we learn how information about appearances is locally shared instead of trying to learn the entire distribution of appearances. In the two-view setting, we benefit from our local point-based representation, resulting in a much higher level of detail. The visualization of the attention of different embeddings shows that the embeddings specialize on similar regions of the category and represent symmetries as well as general self-similarities. Moreover, we show that SimNP learns meaningful latent spaces, enabling disentangled interpolation of the coarse shape in form of the point cloud deformation and the appearance in form of the embeddings. To summarize, SimNP introduces an expressive local representation instead of a global one. By learning how information is shared, we obtain a minimal required data prior. And we achieve this by learning general self-similarities in an unsupervised fashion. Thank you for your attention.